All right, we talked about in general how we can use K-maps to optimize, but it was a little confusing about how we actually can get to them. You still have to, kind of use the force, so to speak, in order to figure out the best blocks to select. So we're going to start talking about how a computer can can create it. Hopefully, I've gone at least enough detail to convince you that a computer or Verilog can take your circuit, and as long as there's only 4 inputs, it can eventually generate a K-map and then populate the K-map correctly. So the next question is, how can a computer or a program take the K-map that's been populated and automatically select an optimal circuit? Well, spoiler alert, it can't select the most optimal one, but it can do a lot to optimize your circuit. The first thing it needs to do is look at what's called a prime implicate, and it's a product term obtained by combining the maximum possible number of adjacent squares in a map into a rectangle with the number of the squares of power of 2. Wow, that was a mouthful. In other words, remember how I was over here on the board? I selected a square and I was trying to expand it to the largest one. So a prime implicate is what are all of those squares that can be fully expanded. Because you could just select every one square, but that's not useful. We want to see the ones that can be fully expanded. And so that's what a prime implicate is. Hopefully you can see a computer can do that, because you can start at one square and just keep trying different routes until it gets the full square there. And it can go and run that for every single square on the K-map. A prime implicate is called essential if it is the only prime implicate that covers one or more squares. And this is going to make a lot more sense pictorially, but if you have a prime implicate and that's the only one for a square, then it's essential. And the nice thing about an essential prime implicate is it has to be used in the final optimal circuit. All right. And a set of prime implicates that cover all the mem terms includes the min terms. So yeah. All right, so here we go. Let's go look at this K-map on this side. Hey, look, they changed it from WXYZ to ABCD. Same thing, different values. So first off, that's a prime implicate because we cannot grow that anymore. That's another prime implicate. We can't grow it anymore. That's another prime implicate because we can't grow it anymore. And that's a prime implicate because we can't grow it anymore. And that is also a prime implicate. You probably didn't see that at first. But do remember that you can jump across the boundaries. You have to think of this almost as a globe that wraps around. And the corners are as well. All right, everyone see that those are prime implicates here? Those are the largest squares you can get. So the next question is, what are the essential ones? Well, notice that these 2 squares only have one prime implicate covering them. That means that the prime implicate that cover each of those squares has to be an essential prime implicate. So that's prime implicate, and that's an essential prime implicate, and so is that. So you know from here that your optimal circuit from a K-map has to select those 2 boxes. How are we doing? Yes?
So, why is it only those 2 whenever you could also make a line out of CD there? CD is no. Yeah, it's CD, just like the other side. What makes that not a prime implicate?
CD is not a prime implicate because none of the squares it covers it has sole cover of. In other words, every square it covers has another implicate that also covers it. So for example, this one is also covered by, what's that called, not BC. This one is also covered by BD. This one is also covered by AD, and this one's covered by a whole bunch of them, like A, not B. So each of these squares have another implicate besides CD that cover.
So that top left, both the top left corner squares of both the corners in the box, because nothing overlaps with those, that makes it a prime implicate?
Right, because I want to say yes. Let me just use my words for a moment. Right here, there's only one implicate that covers this box, right? So that implicate that covers this box is an essential prime implicate. There's only one prime implicate, that covers that box. So that prime implicate is an essential prime implicate. Okay?
Yeah.
All right. Now, naturally, you look at this, and there are other prime. We doing okay? Yeah.
Yeah.
Okay. And there are a couple of other prime implicates we still need to select in order to fulfill the circuit. But what's nice is you can hopefully see that at this point the computer can just run through and see which squares only have one prime implicate and select those. So we can get the essential prime implicates pretty quickly. Bless you again. Let's find all the prime implicates for this one. Beautiful. Oh, this part gets messy. All right, 0, 2, 3, 8. Where's 8? 9, 10, 11, 12, 13. Perfect. Bless you again.
So we don't care if they're essential for this one, we're just trying to find fine.
Is that what it said? All prime implicates. What are the prime implicates here? Bless you. Well, what covers this whole, these 8 right here? W. Ah, I broke it. Sweet. Z, no, because it's split in Z. It's just W. That's 1. Comma. That's a comma. I know it's hard for me to write from this angle. What's another one? You can choose this one, and can you choose 2 others? Yes. Which other 2? You said yes. Yeah, so we got Y and not, yep. AKA these 4. Is there another one? Oh, we forgot this guy up here.
Yes, you need the corners.
Right. What are the corners again?
Not X.
Not X, not Z? All right. I think that's it for this. I don't see any others. Yep. Pretty sure those are it. All right. And yes.
Do you know how small to make boxes for the pop?
You keep making them until you cannot make them any bigger. So select here, what can be bigger? Well, you could select these 2. Can you make it bigger? Yes. Just say bigger, bigger, bigger. Can you make it bigger? And then once you have those 4, can you make it any bigger? No.
You go back like 2 slides.
I tried to go back on the recording.
Alright, so like the second one, you said it better. Can you make a box that cover all 6 of those ones in the middle?
6? No, you can't do 6.
It can only be 4.
It has to be a binary number. So 1, 2, 4, 8, 16, 32, etc., etc.
Okay.
All right, here we go. Let's see if we can find all 7 of them. Ah, 0, 2, 3, 4, 7, 12, 13, 14, 15. Did I do that right? Okay. There are 7 prime implicates. Ooh. Okay. Who's going first?
WX. The
Okay.
whole row right there.
Yeah, that whole row. So, whoops. Let's see, erase this. That represents this right here. Good. Next. Let's do this. Let me show you systematically how to do it. Let's start here. Can we go right? No. Can we go down? Yes. Can we go over 2? No. Can we go down 2? No. Can we go left 2? No. Can we go up 2? No. So this is the prime implicate of just these 2. What's that to? Not W, not Y, and
Not Z.
not Z. All right. Pop back, because we tried going down. This square going left. Can we go left? Yes. All right, so we're going to check that one and that one. Can we go left 2 more? No. Can we go up 2? No. Can we go right 2? No. So there's another prime implicate right there. What are those 2 corners? Not W,
Not X.
not X,
Not Z.
and not Z. Okay. All right, that's it for that square. Let's go over here. Can we go to the right? Yes. Can we go right again? Nope. Can we go down? Nope. Can we go up? Nope. All right, how about those 2?
Is it Y?
Not W,
Not X.
not X, and then Y. All right. We're still here because we tried going right. Can we go down? Yes. Can we go down 2? Or can we go over 2? No. Can we go down 2? No. Can we go left 2? No. Can we go up 2? No. So these 2 is another one. Those 2. What's that?
Not W. Y, Z.
Yeah, Y, Z. All right. We're still on this square. Can't go left, can't go up. Let's go to this square. All right. Can we go to the right? Yes, but we've already chosen that one down here. So let's pop back. Can we go down? Nope. Can we go left? Yes, but we've already done that one. So we skip it. Can we go up? No. All right, let's go to the next row. We're in this one. Can we go up? Yes, but we've already chosen that. We're here. Do we go right? Nope. Can we go down? Yes. So just these 2. So we have these 2. Can we go right? No. Can we go down? No. Can we go to the left? Nope. There's 0 here. So what's these 2? X. Someone said it. Come on, guys. Loud and proud.
Not Z.
X, not Z.
X. Oh, you're missing one other variable.
Not Y.
Not Y. How many are we up to? 1, 2, 3, 4, 5, 6. Ooh, we need one more. All right, if you keep doing this, the next one is going to be this one and that one. And what's these 2 going to be?
X, Y, Z.
Yep.
Yeah.
Hex Y Z. All right, there are a bunch of prime implicates. Whew, that's a whole mess of them. Excuse me. So for 5 variable problems, we could use 2 adjacent K-maps. The point of this is just to show you that you can extend K-maps into more dimensions than just 4. The problem is after 4, it's very hard for us humans to write them. Of course, the computer doesn't care because it's just numbers that it's storing. So a computer computing on more than 4 dimensions of K-maps is not a problem. We are not going to do 5-dimensional K-maps because that's just annoying. And it serves no purpose, at least in my opinion, which I guess is the one that matters. All right, let me, we'll conclude here real quick. So the last thing to do is in K-maps is sometimes a function table or a map contains entries which it is known. In other cases, it doesn't care if the output is something. Now this is a circuit analysis where it can find out that if you put a certain value after this module, it doesn't matter what that wire is, it's going to ignore it. So you can either make it 1, or you can either have it be the output 1 or have it not be the output. And we signify those with X's. And that means that you can, the X's you may include in any of your boxes, but you're not required to have any of the X's come in the final output. I think this makes a lot of sense in the picture. So here we have, look at those X's. What this does is actually help simplify the circuit greatly, because now for the bottom two, we can just select W as opposed to having to select, if there were no X's, then we'd have to select W and then what would be W, not X, and not Y. But since we have X's right here, we can just select W, which simplifies the circuit. Also, it allows us to extend these two prime implicates down as well and simplifies those addition as well. In other words, we're allowed to have 7 gates up here as opposed to 12 down here, which is what we'd have if we didn't have any don't cares in our circuit. Okay. Hopefully I don't have to go through that. The X's, in this example, the X's were part of the output, but when you're problems, they do not have to be part of the output. You can use them or not, it doesn't matter, we don't care. All right, the optimization algorithm. Find all prime implicates, include all essential prime implicates in your solution, great. The next step is to select a minimum cost of non-essential prime implicates to cover all min-terms not yet covered. That is not an easy problem. That is actually a very hard problem. It's a non-deterministic polynomial. So it turns out we have to use estimation algorithms in order to figure out the rest. We are not going to go over that in this class. It's beyond the scope, because the point of this whole detour was to help you understand what Verilog is doing for you, how much power it can do to help you out, and what some of the limitations are. So a limitation here is that it cannot give you an absolute optimal circuit. A human being still has to sit down and do that if it matters. But since your circuits are having billions, well, quantum processors have billions of transistors, a lot of times the human being only optimizes the parts that actually matter. So that's why you still have in circuit design people designing very specific ones, like the adder usually gets a lot of attention because the adder is a hotspot. It is used all over the place every cycle and used numerous times. While other times, like selecting something or whatever, usually doesn't matter as much, especially if it's an instruction that's only called every once in a while. All right. We don't really care about this. Well, yeah, that doesn't matter. So, oh, okay, good. Let's do a full example pictorially. That's a good. So on the left, they selected all the prime, or made all the prime implicates. And then they determined which ones were essential. Well, this is a box with only one prime implicate, so you have to select that. Select that prime implicate. And this is a box with only this prime implicate, so you have to select those two. Those are the essential ones. And then you kind of run an algorithm. What's the way to minimize the rest? Well, for this box, we can see pretty clearly that it's going to be these two, because there's no other way to increase it. A computer, there's no other way to increase it is not very easy to encode. So a human was able to do this pretty well. Of course, Espresso or other advanced algorithms would probably figure this out as well. But the point is, if this went out to a 5, 6, 7 variable K-map, things get very crazy very quickly. So those are, the essential is what you had, the selected is what you used. So with don't cares, here's a great example of the don't cares where they pick the essential, and the essential ones, or I'm sorry, the selected, the essential was the one in the middle, they selected those two, and in this version, one of the X's was not selected. That's perfectly fine. Just want to make sure you had that picture, or at least an example for you. All right, so I went through this course and talked about how you can automate it. So this slide is not too useful, except for remember there are sub-optimum algorithms, although the optimization is pretty close to optimal. All right, the end. Any questions? Because that's all we're going to do with K-maps and Boolean logic and the don't and all of that. Any questions, comments, screams? Because we're going to jump right back to architecture and Verilog. We good? All right.